encouraging. We just got 8 weeks of school left, and for seniors, less than 8 weeks of school left. Seniors have what, like 5, 6? I think it's 5. No, I think it's 6. Maybe it's 6. Not much anyway. So seniors will not be around here very much longer, which is a lot of you guys, a lot of seniors in this class. But we'll get there. So where's everybody at? We got like half of us here. Not even half of us here. But we'll give it another minute or two. My daughter flew in from New Jersey last night, so she's in town. I'm excited about that. She'll be here all week. Back on Saturday. She's here checking on her business, meeting with a corporate guy. Whatever. I did have some fun over spring break. I took my little grandson bowling for the first time. He's been in the bowling alley lots of times because I'm the bowling coach. So he used to come by there after school. His mom would pick him up from preschool or pick up from his daddy or babysitter or wherever he was, and they'd come to the bowling alley so he could hang out with us. And he loved watching all the bowling, so he got to do it for himself. He's about to turn 2 on Saturday, so he's just a little fella. But he was having a lot of fun. We pulled the dinosaur out there and set the ball on it, and he'd push it off the dinosaur and watch it roll down there. He's very excited about getting to do that. So he's learning how to bowl, and he's learning how to take turns. See, because he's right now he's an only child, so he doesn't know how to take turns. So he was learning when bowling. He would be like, it's like, nope, you got to wait on daddy first. After daddy goes, then you can bowl. Got to wait on grandma. And he got a 99 on his first game. So of course he had the bumpers and he had the dinosaur, but still, he had a lot of fun. It was a good time. It was funny though. I got the lightest ball they had was a 6-pound ball, which is like you can juggle that. It weighs nothing, 6 pounds. And I'd say, here, you want to hold the ball, and I'd hold it down there, and he'd put his hands like this, and then I would lower my hand, and he would go. It's like, come on, I know you're strong enough to hold this 6-pound ball, but in his mind, it weighed 600 pounds. And as I would lower the ball, he would lower it to the ground. And so it's like, okay, I'll help you carry it to the dinosaur then. But yeah, that was funny. It was like, I know you could pick this up. But anyway, all right, it's 9 o'clock. Let's get to going and see what we got this week. Kind of fun stuff we're doing. We're not quite through with matrices. But we're about to wrap it up. I think this is our last week, I'm pretty sure. Let's go to our grade screen and see for sure what we got. We had the sequences early on, a lot of matrix. Yeah, this is it. We're going to finish the matrix unit. Find the inverse of a matrix, use determinant. So find the inverse, and then using matrices to represent systems of equations in quiz number 4. So we're going to wrap it up, starting with finding the inverse of a matrix using determinant. Let's go back here. So basically, we've done quiz 3 before spring break. We need to do these 2 folders and look at quiz 4. So what do we have in here? We have a video lesson, and down here we have a video lesson and another. So we have 3 video lessons and then 3 assignments to turn in. So we'll click on this first one, check this out. Here I'm sharing that in a way that you can hear what he's talking about. Well, I don't know who's on this one. Haven't watched it yet. Here we go.
Let's attempt to take the inverse of this 2 by 2 matrix, and you'll see that 2 by 2 matrices are about the only size of matrices that it's somewhat pleasant to take the inverse of. Anything larger than that, it becomes very unpleasant. So the inverse of a 2 by 2 matrix is going to be equal to 1 over the determinant of the matrix times the adjugate of the matrix, which sounds like a very fancy word, but we'll see for a 2 by 2 matrix, it's not too involved. So first, let's think about what the determinant of this matrix is. Well, we've seen this before. We just look along the 2 diagonals. It's 3 times 2 minus negative 7 times 5. So this is going to be equal to 1 over 3 times 2 minus negative 7 times 5. So minus negative 7 times 5. And then the adjugate of a, and here I'm really just teaching you the mechanics of it. And it's a little unfortunate that in a typical Algebra 2 class, you kind of have to just go into the mechanics of it. But at least this will get us to where we need to go. So the adjugate of a, you literally just need to swap the two elements on this diagonal. So put the 2 where the 3 is and 3 where the 2 is. So so this element right over here, this 3 will go right over there. This 2 will go right over here. And then these two elements, you just take the negative of them. So the negative, let me do a new color. The negative of, actually I'm running out of colors. The negative of that is negative 5. The negative of that is positive 7. So we are left with, this is going to be equal to 1 over, 3 times 2 is 6, negative 7 times 5 is negative 35, but then we have this positive over here, so this whole thing becomes plus 35. So 6 plus 35 is 41. So the determinant of our matrix is 41. We're going to take 1 over the determinant and multiply it times our adjugate, times 2, negative 5, 7, and 3. So we get, so this is the drum roll part, 2 over 41, negative 5 over 41. I'm just multiplying each of these elements times 1 over 41. 7 over 41, and 3 over 41. And we are done.
Hey, so as he said, a 2 by 2 is about as far as we were to go on finding the inverse of a matrix. You can do larger matrices than 2 by 2, but that is no fun whatsoever. So that was a very short video. Let's look at the lesson. I mean, the assignment that goes with that. Oh, they're looking for donations. So you can just close those windows when it comes up. Ready to practice. 4 questions. So let's see what we got going here. Let's go. Consider this matrix. Find the inverse. It says non-integers can be given as decimals or simplified fractions. Give exact values. So I want to write this down because we're going to need to do this on paper because there's a little bit of work to the inverse, but nothing that we can't handle. I took some notes real quick when he was talking about finding the inverse. It's 1 over the determinant times the adjunct of this, which you take the A and the D and swap places, and then take the opposite sides of the BC. So for A, B, C, D matrix, we want to do that. So to find the inverse, 1 over the determinant, which is negative 4 times 6 minus 2 times negative 6. Right? That's the determinant. You take these two and then subtract these two. Multiply these, multiply these. And then that is multiplied by trade places, 6 and negative 4, trade places. And these stay where they're at, but the sign changes. So this becomes a negative, that becomes a positive. All right. 1 over. See, this is negative 24 minus negative 12. So that'd be plus 12. Negative 24 plus 12. So this is 1 over negative 12 times 6, negative 2, 6, negative 4. So our answer is going to be 6 times negative 1/12 is negative 6/12, which is negative 1/2. Right? Negative 1/2. Want to simplify that. Negative over a negative. So that'd be a positive 2/12 or 1/6. Because negative 2 over negative 12 would be cancel out the negatives. Then we got 6 again. So this will be the same as that one, negative 1/2. And then we have a negative 4 over a negative 12. So 4/12, which would be 1/3. So the inverse of this matrix is negative 1/2, 1/6, negative 1/2, 1/3. Let's see if we can't put that in here for our answers. So this is negative 1/2. It says it can be simplified fractions. So we're going to see if this works. 1/6, negative 1/2 again, and 1/3. Let's see if we did it right. See if it takes those answers. Yes, that is correct. All right, so we just have to step through carefully and make sure that we're doing it properly. We don't want to do a 3x3. You can look it up how to do a 3x3 or a 4x4. It is a lot. It'll take a page of paper for that. We can do these pretty simply without a whole lot of paperwork. Let's do the next. So have some paper out because the third one, I'm going to let you guys try it while I'm doing it separately, and then we'll compare answers. But we'll do another one together here. So 1 over the determinant, 2 times 7. I'm just doing that. Negative 2 times negative 8 is 16. All right. And then we trade places, 7 and 2 and positive 8 and positive 2. Okay, so these all are positive when we trade places there and then change the sign of these two. So 14 minus 16 is negative 2. So this is negative 1 over 2, or 1 over negative 2. It's the same thing as negative. This is a negative 1/2 times our 7, 8, 2, 2. So this will simply be negative 7/2, which does not simplify, negative 8/2. Well, that's just negative 4. Negative 2 over 2. Same thing there. So 3 of those end up just to be an actual number when you simplify it. 8 over 2 is 4. 2 over 2 is 1. There's a negative on one of them. So let's put that in as our answer. Let's see how we did. Negative 7/2. Negative 4, negative 1, negative 1. All right, there's 2 down. All right, this one, I'm going to work it, but I'm not going to show you. I want you to work this on paper, and let's see if we get the same answer. I'll show you my answer after you get your answer. But write this one down. Good to practice this. This is something a little different. Okay, I stepped through. I'm not really showed it quite yet. Here, I'll show you the other problems that we did if you're still needing the process of how that works. Like, there's the first 2 that we did together. You need a reminder on the steps. Start with the original matrix. You take 1 over the determinant, and the determinant is diagonally this way multiplied to be negative 24. Subtract these 2 multiplied to be negative 12. Negative 24 minus a negative 12 ends up just negative 12. And then remember for this, you trade diagonally, 6 and negative 4. These stay where they're at, but the signs change. So the 2 becomes negative 2, the negative 6 becomes positive 6. So then you just multiply and simplify. All right, I think some of you have some answers. You're still working on it. Great, still work. But here is my work on this last one. I saw Alexander was on the right path. He put his first row, and that's exactly what I had in my first row. So when you do the determinant, it should be 1/3 because you should get positive 15 because those are negatives multiplied times each other. 15 minus 12. So you should get 1/3 as your number outside the matrix, which I guess we can call a scalar because you're multiplying it. Scalar of 1/3. When you reverse those, you end up with all negative numbers inside the matrix because you swap these two negatives and those you make negative. Then it's just a simple multiply. Unfortunately, it's always a 1 on top. So that makes the multiplication really easy. You just have to simplify. -5/3 is as simple as it gets. -6/3, 6/3 is 2. 6 divided by 3 is 2. So that's a -2. You got -2 times 1/3. That's just -2/3. And then you got -3/3. So -1. So hopefully you came up with those same answers. Great. Let's put that in our website here. Let's see if it likes what we got. -5/3. -2. -2/3. -1. All right, don't forget your negatives. Make sure everything's simplified. Good work. All right, we have one more to do, so I'll let you work on this one as well. I'll work on mine here on the side. 3, 6, -10, -10. That's interesting. We got the same number twice. So, all right, give that one a go. All right, probably still working. That's okay. I was just going to mine. I ended up with all fractions. There's no whole numbers in my final answer. But they all simplify too. None of them are like fractions that don't simplify. You have to simplify all 4 of the fractions. But they are not very difficult to do. It's not like it's 3/51 or something. It's a little easier to work with than that. All right, are you about ready to see my answer? If you're still working, don't look. Keep working on it. I'm gonna put this up on the screen. There's what I got on that one. If I didn't do anything wrong, if you got something different that I messed up, please get me corrected here before we type it in. But I got the determinant simplifies to 1/30th because you have a -30 minus -60. So minus a negative means -30 plus 60. So I got a plus 30. So I got a 1/30th as my outside scalar. And then rearranging the matrix to where -10 is our first item, 3 is at the end, and the other two changed to -6 and +10. Then it's multiplying. You've got the 1/30th times a -10. So you got a -10/30ths, which 10/30th just simplifies to 1/3. So it's -1/3. Then you got 6/30. It's a negative. So we have a negative 6/30 is 1/5. 1/5. 6 goes into 35 times. Then we got positive 10/30th. Positive 10/30. And then we have a 3/30th, which is 1/10. You got 1/3 and 1/10 on the bottom row. That is correct. So yeah, if you had something different, see where you messed up the steps, because it turns out this is correct. So when we're done, I'll take a picture of this, put it in our Google Classroom as well if you want to review your work, if you had any issues. Oh, it's screenshot time. Show my summary. Oh, wait, I didn't paste my. Scroll down, paste my screenshot. 4 to 4. Submit. Don't forget to submit. Okay, so that is the first folder. I'm closing that folder. Solving equations with inverse matrices. So first is representing and then solving. So let's check out this first video, representing linear systems. Get this going here. We've looked at a little bit of this way early on, I believe.
I have a system of two equations with two unknowns here, and we've seen how to solve this, and there's multiple techniques we've used, substitution, elimination, and we could do that right over here. In fact, you could just add the left sides of the equations and the right sides of the equations. The s's would cancel out. Actually, let's just do it to show how that's relatively straightforward for at least this example right over here. You add the left-hand sides. These cancel out. You're left with negative t is equal to 7 plus negative 6 is equal to 1, or you get that t is equal to negative 1. T is equal to negative 1. And if t is equal to negative 1, this top equation, you could use either one, would simplify to 2 times s. Negative 5 times negative 1 is plus 5. Plus 5 is equal to 7 is equal to, let me use those same colors that we have over there, is equal to 7, or, and we could do this part in our head, 2s must be equal to 2, and that s is equal to 1. 2 times 1 plus 5 is 7. And so we have s is equal to 1. So that was pretty straightforward. What we're going to do in this video is represent the same system, but we're going to represent it essentially as a matrix equation. And we're going to solve it using inverse matrices. And I'll give you a little bit of a warning. It's going to be more involved. It's going to take us more time to this. And you're probably going to be saying, well, why are we even going through the trouble of it? And the value of what we're going to do in this video is that it's very useful in computation, where you might solve almost the same system over and over and over again. Maybe the left-hand sides are the same, the right hands keep changing, and this might be something that you might see while writing a computer game or while working on some type of computer problem. And so, and this is a general theme. A lot of the value of matrices are they are ways to represent problems, mathematical problems, ways to represent data, and and then we can use matrix operations, matrix equations to essentially manipulate them in appropriate ways if we're, for the most part, writing computer programs or things like computer programs. So bear with me. You will enjoy it eventually, what we're about to do. And one day you will see that it is actually quite useful. So the first thing we need to see or need to appreciate is that this can be represented by a matrix equation. Now what I'm going to do is I'm going to take the coefficients here. So I'm going to take the coefficients here. So 2, negative 5, 2, negative 5, negative 2, negative 2, and 4, and positive 4. So all I've done is I've taken the coefficients here, and I'm going to claim that that times the column vector st, s, and t, being equal to the column vector, 7, negative 6, 7, negative 6, is the exact same thing as what we have right over here. These are representing the same constraints on the variable s and t. And you say, well, I don't quite get that. And if you're saying you don't quite get that, multiply this out. Multiply this out and think about which entries they need to be equal to when you multiply it out. And you would see, well, this entry, this first row, first column, that's going to be this row. We're going to be dealing with this row and that column. So if you think about it, it's going to be, this tells us that 2 times s, 2 times s, plus negative 5 times t, so I could say minus 5 times t, must be equal to the first entry up here. First row, first column is equal to 7. All I did is I multiplied. I dealt with the first row, first column, and said, well, when I take essentially the dot product of those, and if you don't know what a dot product is, don't worry, we'll explain it other places. It's essentially what I just did here. The first entry here times the first entry, the second entry here times the second entry, and we add them together. That must be equal to 7. But when you do that, you essentially construct this first equation. And when you do it with the second row and this column, you construct the second equation. You get negative 2 times s, negative 2 times s, plus 4 times t, plus 4 times t, 4 times t is equal to negative 6, is equal to negative 6, is equal to negative 6. So hopefully you appreciate that this contains the same information as that. And there's other ways that I could have done it. For example, you could have, instead of writing it this way, this system is obviously the same thing, as, and actually let me just copy and paste it, is the same thing as, so copy and paste is the same thing as this system, where I'm really just swapping. So once again, copy and paste. Obviously I've written the second one first and I've written the first one second. So this is obviously the same system. And so if I wanted to construct a matrix equation with this system, I would just swap all of the rows. The first row here would be negative 2, 4. Well, I would swap the rows for the coefficients, but I would still keep the s and t's in the same order. And you could do that. Try to represent this right over here as a matrix equation. You would have the matrix here would be negative 2, 4, 2, negative 5, and this would be negative 6, 7. But now that we've set this up, how do we actually solve something like this? Why do we even do this? And to think about this, let's actually think about it in terms of literally a matrix equation. So let's say that A, the matrix A, is this thing right over here. This thing over here is the matrix A. Let's say that this right over here, this is the column vector x. And so I'll write it as a vector x right over here. So you have the column vector x. And then this right over here, you could say that this is equal, and let's call this the column vector b. So this is equal to the column vector b. So we're essentially saying that A, the matrix A, times the column vector x is equal to the column vector b. Let me write that again right over here just to emphasize it. The matrix A times the column vector x is going to be equal to the column vector b. And so this is what they're talking about when they say a matrix equation. And actually, even before we even think about computation and computer graphics and all of that, you will see a lot of things like this in physics, where they're speaking in general terms, where they might not even be specifying the dimensions of the matrix or the dimensions of this vector, but they're talking about some general property in, say, physics. And so you'll see matrix vector equations like this a lot as you get into higher and higher sciences. But once again, let's just go back to our core issue of how do we actually solve this? Well, one way you could think about it, we've already seen that if a matrix is invertible, that means that there's a matrix A inverse that exists such that A inverse times A is equal to the identity matrix. So what if we multiplied the left-hand sides of both sides of this equation by A inverse? Remember, order matters when we are multiplying matrices. So we multiply the left-hand sides of both sides of the equation by A inverse, which would get us A inverse times A times x is equal to A inverse. Remember, I'm multiplying the left-hand sides of both equations. A inverse times the column vector b. Now, why is this interesting? Well, we just said that the inverse times A, assuming that A is invertible, that this right over here is going to be equal to the identity matrix. So that's going to be the identity matrix times column vector x, and that's going to be equal to this stuff. That's going to be equal to that. So let me just copy and paste that. That's going to be equal to that. Now, why is that interesting? Well, the identity matrix times some other matrix, this column vector essentially is a 2 by 1 matrix. That's just going to be this column vector again. So it's just going to simplify to that our column vector is equal to the inverse matrix times our column vector, or our column vector x is equal to the inverse matrix times the column vector b. And so once again, emphasizing why is this useful? Well, yes, you do have to go through the trouble of calculating A inverse, but once you've done that, you could keep swapping in different b's. You know, this one is 7, negative 6, but you could have other b's here. And if you're running a computer program, you want to do this over and over again, you just have to do multiple matrix multiplications. So I'll leave that thought here. I've realized that I'm approaching 10 minutes, which I never like to cross in these videos. In the next video, we'll actually compute what A inverse is and calculate what the solution vector x is.
All right. That certainly looks like something that's going to require some practice, but let's see what our assignment is that goes with this. Are we just figuring that out, or let's see. Okay, so that was representing linear systems. So now we need to look at using matrices to represent systems of equations. Assignment. Let's see what our assignment going to look like. Kind of intrigued here. Ready to practice. Consider this systems of equation. Okay. 8x plus y plus 19z equals 17. 3x plus 6y plus 13z equals -5. 12x plus 16y minus 27z equals 33. All right, this is a pretty big systems of equations here. It says the system can be represented by the following matrix equation, where A is a 3 by 3 matrix, and then this is the variable matrix, and B is the 3D vector that is these over to the side. So it wants us to figure out with this system of equations, what is our A, B, and or A and B? Well, A is just taking the coefficients. 8, 1y, 19z, 3x, 6y, 13z, 12x, 16y, -27z. And then the B vector that he talked about is just the what it equals, the numbers that it equals, 17, -5, and 33. So see how we did that? It separates out the variable vector here, the 3 by 1 matrix. We just have to take the coefficients of each of the x, y, and z to where we put the x's all in this column, the y's all in this column, the z's all in this column. 19, 13, -27. And then the constants have their own 3 by 1 vector over the side. Let's check. Okay. This isn't so bad, just converting this into the matrices. Next question. Exact same thing. I'm going to make this just a little smaller where we can see this all on the screen at one time. So you are going to pick an amphibian of your choice. Okay, so we have this system of equations. Now this is just a little trickier because if you notice, this is an x and a y. This is an x, a y, and a z. This is an x and a y and a z. So maybe this will be easier to start at the bottom. Let's do the bottom row. 3, 2, oh, that's not a 2. And that is a -1z, right? -1 is the coefficient of z. Move up to the second row. X is 12. Oh, I put it in the wrong one. Y is 10. And again, there's a -1 for the z. Now remember, in this first column is all the x's. Well, for the first equation, the x is a coefficient of 20. The second column is the y's. Y has a coefficient of 18. And the third column is the coefficient of the z's. Well, the coefficient of z for our first equation is 0. There are 0 z's. That's why we didn't write z in the first equation, because there are 0 of them. But we have to account for that in our matrix. We have to make sure and include our z column, which is 0. And then this is going to be 48, -6, -9. Just simply copying those numbers straight down into its own little 3 by 1 vector. All right, let's see if we did that right. Absolutely. All right, continue on. All right, look at that. This one's simpler because every one of them have an X, Y, and a Z. So this is a simple copy it down. 10, 11. Just don't forget the negative. If there's a minus there, you need to make sure you don't forget that negative in front of your 12. Same thing on the second one. We've got two negative coefficients to deal with. So in the second row, we got 6, -8, and -2. And then also two negatives on the third row, 4, -6, -8. And then we just simply take our three, what that boxing, right? Take our three constants and put them in their own vector over here. -18, 10, 12. And only one of those is a negative. Does that look right? So I like to go back and double check that I got the negatives right. -12 and -18. All right. -8, -2, -6, -8. Okay. It looks like I got all the negatives in the right place. Because that's where a lot of times it's easy to make a mistake. You forget to put the negative, and then you miss the whole problem. All right. So what is the first row? Here, I'll open up the chat. What is our first row of matrix A? Matrix A. What are we putting in our first row? Three numbers. We need three numbers for first row.
Colorado ours would hang out right there. We would open that up and oh, man, y'all are gonna die when she's sold. But those are good places to find. So first part, find a local body of water.
You got it?
Okay. Someplace deep. Record some recent information. Okay? And then find a species. And then I want a picture of you at.
Put that in the chat. What's our first row for our matrix A down here in our answer line? I'll make sure you can do this so you guys can get 4 out of 4 the first time.
Give me a drawing. Tell me how everything comes crashing down.
Oh. Okay, this is weird. You're still looking at problem 3 where my screen is showing problem 4. Let me see what's going on with that. I don't know why that froze up, but we entered the answer to 3 and went to 4. So I have a new problem up here. There we go. I don't know why it's freezing up on you. All right, look at that one and tell me what the first row is. You guys are right for the last problem, but I had entered that and gotten it right. That's just weird.
You're stressing me out about your grade, I think.
Okay, what's our first row on this matrix then? All right, I see one answer out there. Anyone else?
Remember when you go to that place area,
Everybody just going to rely on the one answer that's been given? I just asked that because there's a problem with it. Uh-oh. How many X's do we have? We do have 2 X's. How many Y's do we have? There are 3 Y's. How many Z's do we have? We have 1 Z. There is a Z there. The coefficient is 1. We don't write a 1. But we do have a Z there. So that is a 1.
Oh, yeah.
The second row, we just got to make sure we get the negatives in there. -3, -9, and a +2. But that there's a reason I'll let you guys do that, because a lot of times we get that in our head. If we don't see a coefficient, we want to put 0. And it's not. If there's a variable there, there's an invisible 1 that we omit. We don't put that 1. And on the third line, that's a -1 for the Y. -Y means it has a coefficient of -1. But again, -1 is unnecessary. We just put the negative. And then this is, of course, just copying those 3 numbers straight down. All right, so make sure catch those hidden ones, and then you make sure you get your negatives right. Let me get my screenshot up here again.
So make sure you're double checking your grade.
All right, confetti. Okay, scroll down. Screenshot. Submit.
So your choice, you are.
Okay, we're through with that now. Let's look at this last video, and then we'll look and see what the quiz has to say. But we're going to actually solve, and I don't know if we do that in the quiz or not. That's why we need to look at it. I don't remember. But this will go ahead and take that next stop. We don't have another assignment on Con after this. Notice this is our last thing. The quiz is here on Buzz. So we will not have another Khan Academy assignment, but we do have this video lesson right here on solving. So this will probably take a bit of paper.
We saw that we could take a system of two equations with two unknowns and represent it as a matrix equation, where the matrix A are the coefficients here on the left-hand side. The column vector X has our two unknown variables, S and T, and then the column vector B is essentially representing the right-hand side over here. And what was interesting about it, then that would be the equation A, the matrix A times the column vector X being equal to the column vector B. And what was interesting about that is we saw, well, look, if A is invertible, we can multiply both the left and the right hand sides of the equation, and we have to multiply them on the left hand sides of their respective sides by A inverse, because remember, when matrix multiplication, order matters, so we're multiplying the left hand side of both sides of the equation. If we do that, then we can get to essentially solving for the unknown column vector. If we know what column vector X is, then we know what S and T are, and then we've essentially solved the system of equations. So now let's actually do that. Let's actually figure out what A inverse is and multiply that times the column vector B to figure out what the column vector X is and what S and T are. So A inverse is equal to 1 over the determinant of A. The determinant of A for a 2 by 2 here is going to be 2 times 4 minus negative 2 times negative 5. So it's going to be 8 minus positive 10. 8 minus positive 10, which would be negative 2. So this would become negative 2 right over here. Once again, 2 times 4 is 8 minus negative 2 times negative 5. So minus positive 10, which gets us negative 2. And you multiply 1 over the determinant times what is sometimes called the adjoint of A, which is essentially swapping the top left and bottom right, or at least for a 2 by 2 matrix. So this would be a 4, this would be a 2. Notice I just swapped these, and making these two negative, the negative of what they already are. So this is from a negative 2, this is going to become a positive 2, and this right over here is going to become a positive 5. If all of this looks completely unfamiliar to you, you might want to review the tutorial on inverting matrices, because that's all I'm doing here. And so A inverse is going to be equal to, let's see, this is negative 1/2 times 4 is negative 2. Negative 1/2 times 5 is negative 2.5. Negative 2.5, and negative 1/2 times 2 is negative 1. Negative 1/2 times 2 is negative 1. So that's A inverse right over here. So now let's multiply A inverse times our column vector 7, negative 6. So let's do that. So this is A inverse. I'll rewrite it. Negative 2, negative 2.5, negative 1, times 7 and negative 6. Times, I'll just write them all in white here now, 7, negative 6. We've had a lot of practice multiplying matrices. So what is this going to be equal to? So the first entry is going to be negative 2 times 7, which is negative 14, plus negative 2.5 times negative 6. So let's see, that's going to be positive. That's going to be 12 plus another 3. So it's going to be plus 15. Plus 15. Negative 2.5 times negative 6 is positive 15. And then we're going to have negative 1 times 7, which is negative 7, plus -1 times -6. Well, that is +6. And so the product, A inverse B, which is the same thing as the column vector x, is equal to, we deserve a little bit of a drum roll now, the column vector 1, -1. So we have just shown that this is equal to 1, -1, or that x is equal to 1, -1, or we could even say that the column vector st, s, column vector with the entries s and t, is equal to 1, -1, is equal to 1, -1, which is another way of saying that s is equal to 1 and t is equal to -1. And I know what you're saying. I said this in the last video, and I'll say it again in this video. You're like, well, it was so much easier to just solve the system directly, just with using elimination or using substitution. And I agree with you. But this is a useful technique, because when you are doing problems in computation, there may be situations where you have the left-hand side of the system stays the same, but there's many different values for the right-hand side of the system. And so it might be easier to just compute the inverse once and just keep multiplying this inverse times what we have on the right-hand side. And you probably are familiar with some types of you have graphics processors and graphics cards on computers, and they talk about special graphics processors. What these are really all about are the hardware that is special purpose for really fast matrix multiplication. Because when you're doing graphics processing, when you're thinking about modeling things in 3 dimensions and you're doing all these transformations, you're really just doing a lot of matrix multiplications really fast in real time, so that to the user playing the game or whatever they're doing, it feels like they're in some type of a 3D real-time reality. So anyway, I just want to point that out. This wouldn't be if I saw this just randomly, my instincts would be to solve this with elimination. But this ability to think of this as a matrix equation is a very useful concept. One, actually, not just in computation, but also as you go into higher level sciences, especially physics, you will see a lot of matrix vector equations like this that kind of speak in generalities. And it's really important to think about what these actually represent and how they can actually be solved.
Okay, so that went through the actual solving of that matrix. And interestingly enough, it got the same answers that he did when he just solved the systems of equation, 1 and -1, which it should. If the matrix represents the systems of equations, you should come to the same answer that way. And yes, in this case, it would have been easier to solve the systems of equation rather than convert it to a matrix. But as he said, if you have a bunch of those that are equal, same the same equations but have different values they're equal to, it may be quicker in some cases just to do it the other way. All right, well, let's look at the quiz so we know what's coming up with that, and then we'll be done here. Okay, this is just like the last assignment we did. Consider the system of equations. What is A and what is the vector B? So you're just taking the coefficients and you're taking the constants. Don't have to solve it, just have to convert it. Here's another one. Take this system of equation, convert it into the A and B vector. Here's another one. So there's 3 of them in a row. We're just converting it. And so it's very simple. We don't have to solve any of them. None of them do you have to go through. You don't have to go through that last video steps of actually getting to a solution. We're not going to make it do that. But can you convert them and get it set up to where that would be the next step, would be to do the solution. So 4 problems on quiz 4. That's not bad. That makes that one's pretty straightforward. So you got the 2 Khan Academy assignments to copy and paste your results. The 1 quiz that is in Buzz, and then we are done with matrices. We will move on to something else next week. So if you're behind any of them, and very few of you are, very few of you, most of you guys have been right on pace for all this matrix work. But if you are behind in any of it, get that caught up in a hurry. So that way April It's going to be smooth and easy. We got a lot of testing coming up in April, so our schedule is going to be kind of messed up. I know there's Atlas testing for some grades and all kinds. Maybe some work keys. Sometimes there's work keys in April too. But anyway, with all the testing this month, there's going to be some weird schedule changes towards the later part of April. So don't get behind because you'll get crunched up with all this weird schedule stuff. So need any help? Come see me if you're on RTI for Thursday, which I'm not sure anyone is in here. We'll see you then. Otherwise, have a great week, guys. We'll catch you in April.